This is lecture number 18. In this lecture, we are going to talk about state feedback control. The concept covered in this lecture: implementation of state feedback PWM control, then linking current mode control and state feedback control, then alternative form of state feedback control, then multivariable state feedback control in intermediate bus architecture, and the observer based state feedback control. So, particularly these three parts I want to give just kind of glimpse, because it will take multiple lecture to go detail into this, but just a glimpse of this. But I want to focus on this particular two aspect and want to show MATLAB simulation case study. So, state feedback fixed frequency control. If we take a DC-DC converter and here we are considering a resistive load, in this converter if we consider this is my error current, if we consider inductor current, because in current mode control we also sense inductor current, and it like if we are talking about a buck or a boost converter, there are two state variable, because we have one inductor, one capacitor, and generally we take the current through the inductor as a one state variable and the voltage across capacitor we take another state variable. In this case, since we are taking output voltage, which is more or less same as the capacitor voltage. Okay. If there is no ESR, then both are identical, but in presence of ESR they are very close to each other. So, if we consider output voltage feedback, and then in a switching converter we generally design for regulatory purpose. So, output voltage regulation is one of the objective. So, we need to regulate the output voltage at Vref, which is the desired reference voltage, and we also in state feedback control we also take inductor current as one of the state, which we measure using a current sensor, and this inductor current can be compared with the reference current, and then the error current, this is the error voltage, error current and error current voltage, they are multiplied by their respective gains. For in case of current feedback error, we multiply with the current loop gain, and for a voltage feedback we multiply with a voltage feedback gain. Then the total sum of this is the control voltage or equivalent control voltage, and which actually goes into a pulse width modulation block, and the job of this PWM block is to generate a gate signal Q using the control voltage. Okay. And we have discussed this PWM block in case of trailing edge modulation. We generally consider the control voltage with a short root waveform, and then output of the comparator we use output of the comparator is connected to a latch circuit, and that latch circuit output is used as the gate signal, that we have discussed earlier. So, in this control current mode control, what is the structure of the PWM block for state feedback control, as well as I will talk about the current mode control, that I will discuss using a MATLAB Simulink model. So, here Kc is the current loop gain and Kv is the voltage loop gain that we have discussed. That means, our control voltage consists of Kc into Iref minus IL plus Kv into Vref minus V0. While this is known, because this is the reference voltage which is given by the designer, that we need to regulate at this voltage, but this is something that we have to find out. What is Iref? Who gives us Iref? Is it really Iref is given by someone else, or we need to derive Iref from some other variables, that we will see. But in case of LED driving application, when we want to regulate the current through a LED string, sometime the use of these two architecture, both current and voltage mode configuration, can help to significantly cut down the flickering current. So, I am not going to that, but sometimes this structure can be used where the Iref can be available, because in case of LED driving, Iref is nothing but the nominal current of the LED string, and where Vref can be used as the nominal voltage of the voltage across the LED string. So, now we are going to augmented state feedback control. What is this? So, in our earlier study, that resistive load, so this should be negative sign. In our earlier study, what we consider resistive load, where we took inductor current as a state variable, output voltage as a state variable, and which is here. But there are some changes. So, if we consider our earlier case, our Vcon was Vcon, I can say dash, which was our earlier Vcon, was simply current loop gain. There was a reference current minus inductor current plus we took a voltage loop gain where we consider Vref minus V0. So, this was our earlier, but the present case, in our present case, if we look at this structure, what is there? In our present case, Vcon, we are taking same current loop gain, which is here, into minus L. That means, we have dropped Iref is set to 0 here in this case. Then next plus kV, here it is Kp. So, earlier it was kV, that means there is a gain Kp, which is Vref minus V0. So, this is the same thing, only instead of kV we are writing Kp, that remains same. But now there is a third variable, because there is an integrator, right, and we can assign these states to be an augmented state. First of all, why do we need an integrator? Because in earlier case, if you look at the earlier case, if we want to track a step reference in the output voltage, step change in the output voltage, we cannot ensure 0 steady state error, because there is no integral action. Now, in order to track the output voltage accurately, we need to introduce an integral action, and that is basically introduced after the error voltage. Once you introduce an integral action, then this increases the order of the system, because one integrator increases one order by 1, and the output of the integrator, in fact, if we recall our initial model development, 1 by S term was added in order to realize the dynamics of the inductor current, as well as another 1 by S term was used in order to realize the capacitor dynamics, because there was one inductance has a dynamics, capacitor has a dynamics. Similarly, 1 by S will also have a dynamics, and output is Xa. So, that means we have a third variable, which is Ki into Xa. That means, now in this configuration, our x1 is IL, x2 is V0, and x3 is our augmented state. That means, now if I combine together, I will take a vector which is nothing but x1, x2, x3 transpose. So, this is a state vector, the new state vector, and we can write down all the state space equation in terms of x1, x2, x3 and the other input variable. Okay. So, this configuration is called augmented state feedback control, where we can incorporate the integral action and we can achieve 0 steady state error in the output voltage. And the remaining structure is same. There is a modulator which convert this control voltage into a gate signal, and which is actually going to control the DC-DC converter. Now, in current mode control, if you look, because we know the current mode control implementation, where there is one loop which is the inner current loop, and there is another loop which is the output voltage loop. This is the output voltage loop. That means, output voltage is compared with the reference voltage, and this gives us the error voltage, and then error voltage, actually error voltage is the input to a voltage controller of the current loop, voltage controller, Then the controller output generate a reference current and which is compared with the inductor current, and then this will be error current. This error current actually goes inside the PWM block and then it translates this error current into a controllable gate signal. If we do not consider any ramp signal, then this error current is directly compared, with 0. But if we consider a compensating ramp, then this is replaced by, this 0 is replaced by our sawtooth waveform. Sorry, it is replaced by our sawtooth waveform like this. Okay. So, 0 is replaced by the sawtooth waveform, and this is a comparator here. So, this is a comparator here, and then it has output of the comparator goes to the latch, and that we will see in the MATLAB simulation. So, that means for a PI voltage controller used for current mode control, it is well known. And what is the structure of this voltage controller? That means PI voltage controller is used for a current mode control, where our voltage controller is K voltage controller gain plus voltage controller integral gain by S. So, this is a PI controller. Sometimes we use also type 2 compensator. Okay. So, this is a structure of the IREF can be represented by in this form. Now, we want to make an analogy. Can we frame this current mode control into a state feedback control? Because in current mode control, we also senses both inductor current and output voltage, which are considered to be the state of the system. In state feedback control also we will sense inductor current and output voltage. So, whether they are same or they are different, or can we frame one into the other form or not, that is what we are going to discuss. In state feedback control, we saw the control voltage can be represented by the voltage gain into error voltage and current gain into error current. In current mode control, our control voltage is simply a reference current minus inductor current, where reference current was generated from a current voltage controller, which is a PI controller with a proportional gain of kVp and kVi, that means voltage controller proportional gain and voltage controller integral gain. And we have shown in this paper, if we set the kV, that means the voltage controller gain, if we set to proportional gain here, and current controller gain we set to 1. And then IREF in this case, if you set to integral into this controller, then if we take the right side, if we consider this kVp to be proportional gain, that means this term and this term they are matching exactly. Next, IL is already there, so it is already there because we took Kc equal to 1. Next, kVi, so kVi is set to Ki, because this is the integral gain which is used here. Then both will look identical. That means it is just by taking the right variable and mapping between them. Now, the question is, why do we need to do that? Because we want to, using augmented state feedback form, although it is a current mode control, I want to show in subsequent lecture that this will give us an additional degree of freedom, and because in current mode control we generally use an approximate first order model for the design, and in which we assume that inductor current dynamics is much faster and we just play with the capacitor voltage dynamics. But in state feedback representation we have both the dynamics, so we can better play and we can better separate the loop, and particularly when there is a loop interaction in current mode control, we see the state feedback control can significantly it is very helpful to solve this loop interaction problem. That is another thing. Another aspect we will see in subsequent lecture, for a non-minimum phase converter, the bandwidth, closed loop bandwidth using traditional current mode control is limited due to the trade off between phase margin and that bandwidth, because we need to also achieve a desired some particular phase margin, that means around 50 to 60 degree phase margin. But due to the right of plane 0, that put a limit on the bandwidth. But if we use a state feedback control, we can better trade off, achieve a higher bandwidth compared to output feedback approach, that we will see. But in this discussion, we want to create a simulation case study. Let us go back to the simulation model. Here we are showing a peak current mode control, and this model is here. We have discussed enough about this current mode control, and this is our standard buck converter, which is already discussed, and here we are making a load transient, and we have discussed in the previous lecture, that lecture number 16, that we can create these step transient cases in order to simulate, and delta I 0. That means we are using a resistive load, and after certain transient time we want to introduce a step load transient, which is a constant current load with a value of delta I 0, and that will appear after t step time. That means we will not put at the beginning, after some time we want to introduce a step load transient in the current. And in the closed loop, I want to show, this is a modulator block. If you recall, in our configuration of state feedback control, we have used the current loop gain into current error, we have used voltage loop gain into voltage error, and then we have added them together, and then it is compared. Now, if we set the reference ramp to be 0, then it is the case of current mode control I will show, where there is no compensating ramp. If we add some small amount of ramp, then that ramp, this summation of these two control current and control voltage addition, they will actually get compared with the ramp signal. So, this particular block is basically our PWM block. Next, if we want to realize state feedback control, that means we have to set Kc and Kv, and I have told you in current mode control we use a PI control as the voltage loop, because this is the error voltage, this is the output voltage, this is the reference voltage, this is the error voltage, and you take the error voltage as the input to the PI controller, and the output of the error voltage is the Iref, we call it as a Iref. That means this is the reference current. So, this is our reference current, and this reference current is compared with the inductor current. This is my inductor current, and then the inductor current and reference current, that generates the error current, and we multiply with Kc. Now, in state feedback implementation, what we want to do? We can simply keep all the controller to be 0 and it simply compare, but we need to set some reference current. So, what should be the reference current? And I told you, in current mode control, we will keep the current loop gain to be 1, voltage loop gain to be Kp, and for the PI controller, the voltage loop proportional gain will be set to 0, because already that is taken care here, and current loop Kvi integral gain is set to Ki. So, let us go back and check the same parameter. So, initially I am taking a very small ramp 1, my Kc is 1, Kv I can set to Kp, that means I want to set a proportional gain. Let us first fix our proportional gain. My Kp equal to, let us say 120, my Ki equal to something like this. So, in current mode control, we take this to be Kv equal to 0, we can simply take a PI controller from there, or we can take, if we go back, we can take this to be our proportional control, because it is error voltage. So, that means our Kv equal to Kp, and this KVP equal to 0 and voltage error is simply Ki. So, this is our standard current mode control in which we are taking this architecture. Okay. Hold on. That means in case of this is the current mode control, Kc is set to 1, this is set to 1 for both the cases, and if we consider a standard current mode control, then our inductor current is directly compared to the reference current. So, we do not need additional voltage loop because that is already taken care here. So, in case of current mode control, we will simply set this KVP equal to Kp because it is the outer loop voltage loop Ki, and this Kv equal to 0. This is our current mode control structure and we want to show the result. So, this is our current mode control result. Now, we want to compare this result with our the same state feedback approach that we discussed, where we will take Kv to be Kp, this to be 0, and because in state feedback control what we discuss, this will generate Iref, which is the integral of the error, and so we have a current loop gain, that means error current, reference current is generated as the integral of the error subtracted by the inductor current, then into current controller gain, and the voltage controller gain is set to Kp. Okay. So, voltage controller gain is set to Kp and we want to run the simulation again. And they are exactly identical because they overlap with each other. Okay. But in current mode control, suppose if we do not incorporate ramp, suppose we set ramp to be 0, and in current mode control we set this to be 1, this to be Kp, and let us run it for current mode control. Okay. So, here we are not considering any ramp. Now, we are putting a ramp magnitude of 2 and we are using solid line, and here we are setting Kp and here we are setting 0. Okay. So, here let us see that what happened, that two architecture. So, if we go to the inductor current waveform, there can be slight change, very insignificant change, but I will check it. Yeah, there is a slight change if you take this dotted curve. Okay. So, that means the state feedback control and the current mode control almost resemble each other, and in state feedback we have added an additional ramp sawtooth waveform, okay, whereas in current mode control there is no sawtooth waveform, they are closely same. The next task is that in state feedback control we can simply set another current reference and we can simulate, right. So, that means we can get an equivalent analogous. Now, this state feedback approach is very useful, particularly when you are dealing with this intermediate bus architecture, in which we consider an intermediate bus converter, which is a source side converter, and a POL converter, which is a load side converter. And we discussed in lecture number 16 that in order to provide active damping, we consider current mode control for IBC as well as current mode control for POL converter. So, when we talk about current mode control, that means we can transform this realization into a state feedback form, and the same thing is for the POL converter. That means in case of current, that means in state feedback form we can again generate a reference current for the IBC, and this is my error current, this is my error current, this is my error voltage, and we can also, that means it is compared with my inductor current 1, and for this reference 2 I can compare with inductor current 2, and similarly I can compare with the reference one for output voltage 1 of the IBC, and Vref2 is the reference voltage for the POL converter. I can compare with the, it is compared with the output voltage of the POL converter, and so we will generate the error voltage. Then what do we do? How do we generate IREF1? So, IREF1 we discuss in current mode control can be generated by the integral action of the error voltage of the that particular error voltage of this. That means, if we take this error voltage, this can be IREF1 can be simply some integral 1 into error voltage of VE1 d tau, right. Similarly, I can generate IREF2 by the integral of this error voltage 2, and we can represent into state feedback form. Once you represent into state feedback form, now we have a Kc1 which is the current loop gain of the first stage converter, then it also has a voltage loop gain, current loop gain of the second stage converter, and the current loop gain of the voltage loop gain of the second stage converter. These are all error current, error voltage, error current, error voltage. And then we can, so this is one way of control in which we are generating the gate signal of the IBC by its own loop. That means, its own inductor current feedback and own error voltage feedback. Similarly, we are controlling POL converter by its own feedback loop. Okay? So, that is why it is called 2 single degree of freedom. For each case there is a 1 degree of freedom, because only one control variable is Q1. But since we can represent into a multivariable form, we can actually represent this into a standard state feedback form, in which it is a two input 2 output system. There are 2 output voltage and 2 input Q1 and Q2, and there will be self term which is like a Kc1 and Kv1, and there will be cross term which will be Kc21, Kv21, because the first loop, the first converter gate signal can be generated by taking the feedback of its self current and voltage as well as the other converter current and voltage error information. Similarly, the POL converter output can be generated by the combination of its own current and voltage as well as the current and voltage error of the IBC. So, by this multivariable control, because whenever we do this single 2 degree of freedom 1 degree of freedom control and 2 single like a 2 different, then we do not take into account the coupling effect, and this can introduce a coupling effect and we may not be able to handle properly. But if we represent into this multivariable form, then we can actually take care of this coupling effect by means of state feedback representation and suitably placing the closed loop pole, so that we can attempt to decouple the two systems, provided that they are time scale separated. The alternative form of state feedback control, that means instead of inductor current, we can also use the derivative of the output voltage as the derivative of the output voltage to be another state. In this case, we may not need a reference current, because for a buck converter, the derivative of the output voltage actually carries the information of the capacitor current, so which itself averages 0. So, we do not need to take any other reference voltage. So, we can straight away take this current, that means this is a negative capacitor current, and that can be added up. And we are already taking that means this part is common, but now instead of earlier inductor current, we are simply taking the derivative of the output voltage, which will represent the capacitor current. But it may not be true for a boost converter, where the direct derivative of the output voltage is not recommended, because the boost converter has discontinuous output voltage ripple, and that can induce or inject significant switching noise into the closed loop. And if we want to, if we put a low pass filter, then we actually cannot capture the high frequency current information, because we are actually putting a low pass filter. So, it will attenuate the high frequency current information. So, the direct derivative may not be a suitable choice for a boost converter, but it could be useful for buck converter. Now, we can design observer based state feedback control, in which our output voltage can be sensed directly, but the inductor current can be estimated. So, you can use a reduced order observer. Now, there are two ways of designing this observer, or basically the modeling of this system. The one way, we can use a small signal model. Okay. If we use small signal model, then the whole converter model can be realized into a linear time invariant system form. Whether it is a Perturb dynamics form, we can represent, and then we can use our traditional reduced observer theory to estimate the inductor current information. But this technique relies on small signal, depends on the small signal model, and we know that if we want to increase the bandwidth of the system, then there is a model limit on the control, because the model may not be valid when the perturbation in the duty ratio is large, and that can significantly deviate the actual behavior of the converter. So, this model may not be suitable to design a high bandwidth observer. Whereas, if we use a flux based approach, that means if we take the voltage across inductor and use a nonlinear observer by flux based approach, then we can actually generate the switching ripple information of the inductor current, and by that way we can get a very high frequency current dynamics, and we can estimate the current more accurately, including high frequency dynamics. So, this technique can be used for switching converter, which retain the fast dynamic of current loop, and then we can take the advantage to realize the current mode control architecture, like a advantage of the current mode control feature, but without sensing inductor current, because this is a switching converter. So, linear model may not be a good choice. In summary, we have introduced state feedback control, and I have shown using simulation that link between state feedback control and current mode control using simulation case studies, and we have also discussed about the overview of state feedback control in cascaded converter, where instead of designing individual converters standalone configuration, we can use a multivariable approach to better design a centralized control for better transient performance, as well as the decoupling between the two converter by means of a state feedback approach. And then we also discuss some alternative state feedback control structure. So, with this I want to finish today's lecture. Thank you very much.